Suppose you want to estimate the mean difference when you've used dependent samples. When the data is collected using dependent or paired samples, then you look at the differences. Recall the difference is just the answer to your subtraction exercise. So in this case, you could put the data in two columns and then take the differences from the first column minus the second column, and then you focus your analysis on that column of just the differences. Let's look at example 1 here, where a sports analyst wanted to estimate the difference in mean sprint time in a 40-yard dash between natural grass and artificial turf surfaces. So she obtained a random sample of 50 athletes from local high schools. For each of the athletes, she had the athlete run the 40-yard dash on grass and on artificial turf, and recorded the time in seconds to complete the 40-yard dash. Let's use the results below to estimate the mean difference in sprint times on the two surfaces. Notice the output is using 95% confidence for the level of confidence, and we've got the mean of the paired difference, so we can tell it's paired observations, where the time on grass is first and the time on turf is second. Let's begin by defining our parameter, mu sub d, which is the mean difference in time to run the 40-yard dash on grass and on turf among all local high school athletes. Notice the sample indicated that she only found high school athletes. So these runners were not just anyone, but rather local high school athletes, and that needs to be emphasized. Next, we would want to give our equation and do our calculations. So we start by finding the sample mean difference, d bar, which is listed under the sample difference column in the table. So that is the 0.09423 second value. The standard error is S sub d over the square root of n sub d, and that is 0.007358, and that would be in seconds also. And then the t critical point, if I use technology, I can find it to be exactly 2.010 when rounded to the third decimal place. So using our formula, d bar plus or minus the t critical point times the standard error, we get 0.09423 plus or minus the 2.010 critical point times the standard error, 0.007358, and that gives us 0.079 to 0.109, and again that is in a part of a second. Now if you tried to use table T for 49 degrees of freedom, that's not there, so we could use 50 degrees of freedom or 45. Now for 95% confidence, the two-tail probability would be the 5% not included in the 95%. So the two-tail probability of 0.05 tells us to use this column, and I would want to go down to where my degrees of freedom for 50 degrees of freedom, that row would tell me to use a t critical point of 2.009. Now if I were conservative and used the smaller degree of freedom number that's actually in the table, 45 is the next smaller number in the table compared to 49, which is what I want for the degrees of freedom, I would use a critical point of 2.014. Both of those again are from the 95% level of confidence. So going back to our example, if I use the closer value, the 2.009 critical point still gives me the same confidence interval when I round off to the thousandths digit. If you use the more conservative estimate and go down to the smaller degree of freedom, you still end up with the same calculated interval. So in summary, I could say with 95% confidence, the mean time to run the 40-yard dash on artificial turf is between 0.079 second and 0.109 second faster or lower time than on grass among the population of all local high school athletes. Let's look at another example. Suppose a medical researcher wants to estimate the mean improvement in systolic blood pressure, measured in millimeters of mercury, for patients who have high blood pressure and for those patients who could walk briskly for 30 minutes per day. So she randomly selects 20 patients who have high blood pressure. She records their systolic blood pressure before they start the activity. Then they begin the treatment. So each day they walk briskly for 30 minutes for a period of 1 month. She then has them come back in and records their systolic blood pressure again. Use the appropriate output below to estimate the improvement to the nearest tenth on average among all patients who have high systolic blood pressure, and use 90% confidence in the estimate. So we could look at initial systolic blood pressure readings and see sort of where they are. They run from about 140 to 220. And then systolic blood pressure readings after 1 month of walking briskly each day. We can see that the lower value did go down a little bit, it looks like. It's down to about 110 up to about 200. But really we can't look at the data individually like that because we don't know which person in the initial reading is matched or what their reading is after 1 month of walking. What we really need are the differences. So this is really the graph that we're interested in. And this graph, notice, looks sort of symmetric and mounded. Okay, you've got a tall peak in the center. You've got 3 bars on one side, 4 on the other. So that's within our approximately normal or symmetric at least looking shape. So this is not very different from a normal distribution. As far as the summary statistics, again, we can't look at the initial readings or 1 month after exercising. We've got to look at the paired differences. So we've got to look at this bottom line. So there were 20 patients. The mean difference was 25.65 millimeters of mercury. The standard deviation was 3.498. The standard error, I guess you could use also. I'm going to use the standard deviation. The median and the mean are very close. They're less than 1 millimeter of mercury apart. So that again gives us reason to believe that the mean and median being equal, the data is very symmetric and could almost be thought of as coming from a normal distribution. So let's go back through our steps. So let's define our parameter, which mu sub d is going to represent the mean improvement, or how much reduction there is, or how much is reduced, the systolic blood pressure for all patients with high blood pressure who could walk briskly every day for 30 minutes for 1 month. Sort of give your values and calculations next. So the sample mean, okay, is going to be the difference mean, 25.65. The standard error would be that S sub d over square root of n, so 3.498 over the square root of 20. So I get 0.782177 if I do that. T equals 1.729 comes from table T, where the degrees of freedom is the number of differences, 20, minus 1, so that's your 19 degrees of freedom. And then the two-tail probability for 90% confidence. Okay, 90% to 100% is 10% left over in the two tails. So we would want to go over, find the two-tail probability of 0.10, and then go down the table and find what the 19 degree of freedom row is, and our critical point is going to be that number. So that's 1.729. So then we come back into our equation and we have d bar plus or minus our t critical point times our standard error. So we plug our values in, do the multiplication, and we get 24.3 to 27.0. Then what we would do is write our summary. So with 90% confidence, the mean improvement or the mean reduction in systolic blood pressure among all patients who have high blood pressure who walk briskly every day for 30 minutes for a month is between 24.3 millimeters of mercury and 27.0 millimeters of mercury. Now we can do a validity check. So the confidence interval is valid because we took a random sample of patients and took sort of before and after measurements. So it's paired data. The sample size was n equal to 20, so that isn't large. So I really want to have some indication that the data, as far as the differences, are approximately normal. And remember, we talked about in the histogram of differences, we do have that sort of large peak in the center, almost same number, right? 3 versus 4 categories on each side. Okay, so that's reasonably symmetric, so it's very likely that the differences could be normal. So that assumption likely is satisfied. And then the value of sigma sub d, the standard deviation of the population of differences, is not known, so we're using the sample standard deviation in the analysis. So just to review, on your formula sheet, your confidence interval formula down here is the d bar plus or minus that t critical point times s sub d over the square root of n sub d. The t critical point comes from a t distribution where the degrees of freedom is the number of differences minus 1. The level of confidence, okay, that you're given, you subtract that from 100, okay, or 100%, then find that decimal equivalent number at the top of the column, and that's going to be the appropriate column to use in table T to find your critical point. And then to be valid, okay, the conditions are still the same as we had before, right? You want a random or representative dependent paired sample that's taken. The differences hopefully are stated to be normal, or you have some reason to believe they're normal, and or you need a large sample size, right? And by large we mean 30 or more. And then the population standard deviation, sigma sub d, is not known, therefore you're using s sub d in the calculations. So that is dependent samples estimation of the mean difference.